known scientist, and he's actually a professor at Munich School of Robotics and Machine Intelligence that has been recently established, and we are hearing a lot about his success and new results coming out. And he will talk about physical human-machine interaction and go specifically in some details in some specific topics of his most recent research. And it's a great pleasure. Sami, the stage is yours. Please go ahead.
Okay, great, Arash. Thanks a lot for invitation and to all the organizers to do this in these crazy times. It's a great pleasure to be here. And so, just if you could give me a heads up that it's easy to hear me, that would be wonderful, so that I know everything is fine. Okay, great. Right. So I will probably start sharing my screen, and will then try to abuse my 25 minutes. Okay. All right. Yeah, well, so my title is super generic, and I'm kind of keen to hear some feedback on our most recent work, because we try to kind of put as much as I can into the 25 minutes, and probably will run out of time entirely. But really looking forward and think this is a great opportunity to get into contact while I'm only sitting since I think 3 months in my office and not getting out, not a haircut, nothing. So this is exactly how I look after 3 months of staying in my office. So, and I'm glad to see that you guys are doing well. And yeah, so basically I'm going to start with an example, I guess, on this long trip of physical human robot interaction. I also see Neville joining. So hey, Neville, great pleasure to be in the same session with someone who really influenced a lot of my work. And so I guess just to start a little bit the discussion, I just would like to show you where I guess we are at the moment with physical human robot interaction on real world implementation. So what we have done some couple of years ago was an economic production of robots being assembled by humans and robots in close interaction, having fenceless assembly tasks, and basically making it possible that this whole idea of physical human robot interaction to a certain extent could be commercialized and could be brought into real life, in particular focusing on the mechatronics, control and interaction perspectives in terms of the robot rather being a tool that can be programmed easily and then be set into operation based on its multitude of control and interaction abilities and properties, so that this safe close human robot interaction can in fact be done. So I think what is kind of interesting is that these kind of systems also now become more and more elaborate, and also other fields are kind of thinking about applying such robots in various domains that I personally could not imagine several years ago. But there have been, for example, and I'm intentionally showing something that might be a little bit off the typical PHRI domains, a field where robot assistant and medical applications such as dental care could be something for the future. And I guess this is kind of a short video showing a little bit where things might be going. So, for example, having robots really as an assistant to the dentist, obviously the necessity to having close physical human robot interaction, but also the multitude or multimodal interaction abilities in order to be a tool to essentially non-technical persons, even more than we know from physical human robot interaction in the industrial domain. So for example, kind of being commanded by a speech interface just to give tools that are kind of to be grasped sensitively and the rightful way in order to be kind of handed over to the dentist in this particular example, and essentially being a fetch and carry service that makes it possible to have free hands and to also control yourself, the robot, rather like a third hand. So not yet on the level of full autonomy and so on. However, I think it's kind of interesting that these things can now be done in a way that even totally non-technical people can really do them. And I'm trying to run through kind of some contributions that have been done over the years, but also more recent work. So it's a kind of potpourri of various things, just to give you a kind of teaser in the various direction. And I think it's very clear that the first basis that had to be developed was what I more and more call tactile robots, going beyond classical torque control soft robotics and more towards partially autonomous systems that have some reflexive and tactile interaction capabilities really built into the core of their control system. And we have been obviously pursuing this for many years, far more than a decade, to develop robots that can be grabbed by the hand. You can move them around based on their joint torque sensing, sophisticated control methods, most of it passivity-based control, that then makes it possible to actually have a rather sensitive, safe, and also dexterous system that can be used in principle for assembly tasks, for sensitive assembly tasks that obviously are still a big challenge, and in particular kind of being a tool that the human is teaching and the robot doing certain things in order to autonomously acquire skill. But today I won't talk about our work on skill learning and acquisition, so more focusing on the physical human-robot interaction side of the developments. What I would just like to point out in the work that we've been doing for many years now is really that I think it's very important that we kind of redefine entirely the robot data sheet. So robot data sheets were usually kind of, I mean, apart from all the technicalities that are important to industry, I think it's very important that to a certain extent we go beyond the classical motion tasks that we typically see. So, I mean, next to Cartesian velocity or repeatabilities, path deviations, and so on, which are already quite sophisticated metrics for motion control, I think it's extremely important that we more and more start to think and define and also objectively compare the force sensing capabilities of the systems, and in particular also the interaction capabilities of the systems. And by force sensing, I don't only mean force sensing, but also the closed loop control of these systems. And I guess there is still a lot of work to be done. And we have been proposing some first works in this and also commercially in order to really make robotic systems that are designed for physical human-robot interaction really objectively comparable, including the way to formally measure the concrete application, or the concrete fidelity, for example, in force resolution, in relative force accuracy. So all the things that have not been treated by industrial robot standards, so no ISO standard yet is able to cover these things. So we really try to push forward that these things really have to be measured, reflected, and objectively made comparable between the different systems. So obviously this also goes beyond pure force measurement and force control, but also regarding collision reactions. How do we objectively compare collision reaction? How do we objectively compare worst case reaction times? And also how do we compare the overall compliance behavior regarding its measurable compliance and the deviation from the nominal behavior that we would like to have. Okay, so having said that, I really want to jump more to the collision monitoring, control, and motion and real-time motion planning of things, in order to give you a more hands-on or more concrete overview of the recent work. Just recapitulating what we've been doing in collision monitoring, which probably some of you know. The work we've been starting many years ago, especially together with Alessandro De Luca, also in my time back then at DLR, when we did all the collision detection and reaction schemes for flexible joint robot based on joint torque sensing, and really developing real-time collision monitoring methods that were able to make use of the typical proprioceptive sensing in torque control systems. Having high dynamic ranges in speed, also quite sensitive. What you see here is this video with the contact detection and reaction with sharp objects. And on the left side, the high dynamic ranges. So the collision detection that can be quite reliable even at high dynamic speeds and also accelerations, which made it kind of suitable for various applications. In particular, this also kind of the idea was centered around one central concept. If we look at the standard rigid body dynamics form, then obviously what we are looking for in collision monitoring is the external joint torques in generalized space. However, obviously, now my mouse is back. So if we want to see the joint torques, and obviously they're being projected by the Jacobian transpose in the joint space. However, one fundamental problem used to be that the acceleration is not available. So we cannot just algebraically solve it if we have some joint torque measurements available. let's reduce friction, or let's get friction out of the discussion for a second. Even if we would have the full dynamics model, the main problem in high-speed collision detection was usually that acceleration was not readily available. Therefore, we developed some methods that really solved that issue to a certain extent with Alessandro, and postulated also the so-called collision event pipeline for collision monitoring that basically classifies the collision monitoring into various phases ranging from pre-collision to post-collision, and obviously the first one being the detection phase, then coming to the isolation that essentially tells you where the contact has been taking place along the structure of the system, then identifying the time signal of external joint torques and possibly contact wrenches, and then obviously more and more coming to the higher level of interpretation of sensor signals, classifying the kind of intention of the measurement signal, and then showing the appropriate reaction. So what we have been doing back then was essentially to go into the idea of reformulating the dynamics into the generalized momentum. So essentially coordinate transform, if you want to call it this way. So rephrasing the dynamics into P, which is mass matrix times velocity, and then rephrasing essentially dynamics and setting up an observer. In some sense, you could call it a disturbance observer, a reduced order disturbance observer, that essentially defines the residual dynamics R of first order, that essentially estimates the difference between the observed momentum and the residual momentum. And the interesting thing is, if you basically look at the transfer function coming from external joint torques to R, then you essentially get a forced order constant dynamics PT1 system between true external torques and the residual R, obviously relying on a very good dynamics model, which I guess is kind of obvious, but also on very high dynamic sensing signals, since the filter frequency case 0 is ideally to be set quite high. So with this, it was also not only possible to detect collisions, but to use this generalized momentum observer with some other kind of work, to use it also for very, very accurate force sensing at the end effectors. So what you see here now is basically the force resolution that came from the data sheet I was presenting. So essentially having 1/10 of Newton of dynamic resolution here, static repeatability in force. And obviously also the question about force tracking arises here. So there's many things that can be shown that this method really works to a certain dynamic range. This work has also been extended to humanoids. We're currently working on an ICRA paper to really put the whole thing together, but just to give you a kind of a current view. So this whole collision detection and reaction monitoring system we developed for static manipulators, but we also generalize it to tree-like structures. So having multiple contacts at the different limbs of the humanoid in this example, and being able to also monitor the true forces quite accurately, obviously depending on the dynamics of the impact because of the first order filtered behavior, and this making it possible to really generalize also to more complex systems. However, if we even want to go beyond what I was talking about and really have a system that to a certain extent has even higher bandwidth, higher accuracy and so on, then obviously the major problems in what we've been seeing so far is essentially the work the problem of thresholding, meaning coming from sensor resolution, numerical differentiations, modeling errors, and so on and so forth. But obviously also the low pass filtering in the first order differential equation is really a problem, and therefore we can get up to 25 Hertz, I guess 30 Hertz maybe, of dynamic range of the filter frequency. However, far beyond it's actually not really possible, at least not at the current technological status. So what we have been trying to do is, can we actually propose a method and see can we further push the boundaries on high-speed collision detection? And the result, the ideal solution, as I said already before, is obviously the direct method. So algebraically solving the dynamics equation. Sorry, somehow my cursor always vanishes. I'm not sure I can stop that. So usually basically using the proprioceptive sensing, having the observer-based methods, as I said, there is this lagged behavior inherently in the differential equation. And then obviously the direct method would basically solve the algebraic problem. But as I said, The ideal solution that this would constitute would be very simple to implement, right? So no observer structure, it's straightforward, would have in principle high accuracy and high bandwidth. And the ideal solution would also be with many numbers of sensors. However, as we know, the problem is that we have the numerical differentiation of the position in the joints twice, obviously coming to acceleration, which basically is hard to use at all. And obviously we have the increased uncertainties in R because of large thresholds in filtering. So what have we been doing? We actually proposed recently in a paper we published last year to go to IMUs, use nonlinear estimators, and essentially get very accurate estimates of the velocity and the acceleration, and fuse them into an observer extended direct method variant that then basically is able to have this at least the same accuracy, probably even more of the collision monitoring with momentum observer, but monitor at much higher speed. And I show you the results here. So this is now the solution for a very rigid impact. And what you see here now is in the first one, the true external force measured, then the momentum based, the one with differentiation, so direct method with twice differentiation of acceleration, and then finally the new method that uses basically an extended Kalman observer with IMU and fusing all the proprioceptive sensing. And you can see that even the high speed variance of the signal can be captured by this method, going far beyond the already state-of-the-art method of the momentum-based observer, just by fusing IMU and position measurement in the joints. Together with then later on, obviously, with the collision, with the joint torque. However, on Q and Q dot level, this is a purely kinematic method that doesn't even rely on a dynamics model. So this seems to be a very promising direction to really get high-speed collision detection readily available at some point. So this is a first result we actually recently accomplished. We're quite happy that we could kind of resolve the typical issues we usually have with momentum-based observer. Okay, so the third part I want to talk about quickly is the interaction control, which probably is also most of the things that I'm going to talk about. So obviously we all know the famous work of Neville. So impedance control really being kind of the general framework we're following, establishing second order dynamic behaviors between external forces, wrenches, and the overall behavior of the system. And with this, we can actually get quite reliable compliant behavior that gives the robot the ability to move around even unknown curvatures as it's never seen before, even in dynamically changing environments. So I'm just speeding up so that I'm not running out of time. And even when the environment is changing, then obviously with the right impedance, obviously this is the big challenge, we can then get quite accurate behavior. Other things we could now do, as I was described before, is the force control question. So only with internal sensing, having quite accurate force control, you could see that 7.8 Newton is the desired force. And even for different behavior, different contact patterns like foam or rigid rubber or wood, the robot is able to very quickly converge to the right value. So having impedance and force control obviously have been lots of work in this direction. However, there has been always some limitations, obviously. The nice thing is now that the force control, even with only proprioceptive sensing, can now be done at quite some bandwidth. So this is some force tracking work we've been recently doing, and we can show that only with proprioceptive and the observer extended torque estimation, we can get up to several hertz of force tracking. So at a force measurement bandwidth of 25 hertz. Okay, so then the next problem obviously is that in impedance control, if you want to do indirect force control, then obviously we need to preload a spring. This is a heavy, it's quite some dangerous situation if we preload a spring and don't know that the contact is lost. The same thing happens for force control. So here we can see like the impedance control is preloading the spring, contact is lost, energy is released. The same problem arises if we have force control, as I said before, because obviously the problem of force control is not well defined. So we need to further work on not only having these in well-defined conditions, but getting this together. And we recently proposed, or some years ago actually already, a unified impedance force controller that essentially starts with a very naive version of it, obviously, with some tracking behavior, so the tracking force controller, in fact, and basically defining a PID control loop that then gets embedded into a kind of a passivity-based framework by detecting what we call passivity violating ports, and then augment by the well-known energy tank concept in order to guarantee stability, and then add on top of that a contact non-contact stabilization term that is able then to all together end up in a passivity-based Cartesian force impedance controller. The idea is essentially that we look at the storage functions of the tracking system. Somehow my pointer is not working, but I guess I'm running one by one. So the storage function obviously being the kinetic energy error, the stiffness energy error, and then looking at the storage function and its timely evolution, we can then identify the passivity violating ports, being x dot ff, which is the feed-forward force, or the desired force of the force controller times velocity, the desired velocity and the force controller, and the desired velocity and the external forces. So looking at this time evolution of the storage function actually gives us the possibility to then put together an architecture where we can monitor all these different possibly passivity violating ports, and then obviously pacifying them with the well-known energy tank concept. So I'm not going into details here, but I think it's well known. But obviously there's many things that still need to be done. I'm going to go into this in a second. The result is kind of pretty interesting, that now you can do simultaneous force tracking, even at unknown contact losses. And the robot is then able, under the passivity-based framework, to show very stable behavior, not only in terms of compliance, but also in terms of very accurate force control. So it's actually tracking the forces according to the result we saw before, but is able to deal in a highly stable manner, even with loss of contacts. What you see here now is basically the result, even when a very unstable environment is kind of trying to be tracked. So the robot has no idea about the environment it's kind of following. So what you see here in the upper one is the force error, even during this. Obviously, here you can see the jumps in the environment, but still the robot is able to very accurately track the contact forces up to maybe 1 or 2 Newton, even in these highly unstable and dynamic environments. However, there is one fundamental challenge we still need to, or two, in fact, to still be resolved. Yes, we can do virtual energy tanks to ensure stability. However, it's not yet clear, first of all, the flow between the system and the energy tanks, but also if we have multiple energy tanks, which part of the task do we want to sacrifice first for sake of stability? So we also recently proposed a framework that basically introduces what we call a valve-based energy tank, plus a gain scheduling approach that basically monitors the different energy tanks in the system, and then has a gain scheduler that essentially sets up a priority in terms of changing the tasks in a kind of sequential order, in a prioritized order, depending on a user set preset, obviously. And then what you can achieve, for example, in this, we see in ABC, a robot that is supposed to do a motion task in horizontal direction, a force control task in the vertical direction, and the human basically pushing on the robot. The robot moves from left to right, pushing the weight, and as soon as the human releases, the robot is trying to track the force control task, and obviously using enough energy or too much energy so that the robot stops essentially in the horizontal direction. So essentially showing that you can now have a framework that basically is able to weigh and dynamically change the different weights in the particular task setup, and essentially now have a passivity-based framework with tanks that is able to also prioritize these different tank distributions. This can also be kind of used for power reference learning, essentially meaning that the robot is now not only able to track the task, even if it's not knowing the environment, but actually learning the curvature of the system dynamically. And then maybe the last part I would like to quickly go through for 1 or 2 seconds beyond this kind of desired trajectory of contact learning on collision of real-time motion planning. That essentially is one of the current works we're doing, trying to capture essentially global predictive interaction of collision scenarios into the motion planning. This is work together with Czech Technical University in Praha, with Matej Hoffman and his group. And what we have been doing there is kind of a local and a rather global evaluation of the current, of the potential collision situations, and try to put together a system. I'm going to jump through that in order to give at least time for 1 or 2 questions and go through the experiment, and have a system that is essentially able to fuse 2 methods that essentially look first at the local behaviors. So basically a phase-based controller, so it's compatible with DMPs and other phase-based methods, and can also be integrated into the passivity-based framework. So a system that is able to modulate the phase of the system based on the instantaneous interaction between the human and the robot. That's what we call the orb-based phase shaping. So it's really trying to bring everything together into one variable. I mean, you could also obviously do it via time scaling, but we chose to use shape in order to be compatible to DMPs, another of these rhythmic motion frameworks. And obviously there's also the idea to then use global behavioral or global predictive motion that then essentially can be used to not only slow down conservatively, but actually, I mean, be a bit more cautious, taking into account the global behavior, and then obviously fusing these behaviors that you see here in this example. So if the human is coming too close, then obviously in the first scenario, the robot would basically be stopping in the prognosis window, so the predictive part of the system. The robot could also come into very conservative cases. So what you see here now is basically if the human is now blocking the way, then obviously the robot would not be able to move. And we basically came up with a solution that at least relaxes many of these situations by fusing both cases into one and taking the more conservative one. So only if one of them, if both of them are actually kind of seeing a problem, then the system will stop. So now you can essentially go into potentially dangerous collision scenarios. However, be cautious only if the problem is really in both predictors present, and then try to basically modulate global properties into a single phase of the system that then, and this is kind of work what we're doing now, and I'm skipping that, basically putting it together so that then this can be fed back into the passivity-based tank-based framework, where we then modulate essentially the phase such that it respects energetic requirements that come from the overall system kind of energy considerations, and then try to bring everything together into one single variable, and then is able to control the system also on trajectory phase level, and kind of matching nicely with the passivity-based framework in control. Okay, and I would like to thank obviously all the many collaborators, and probably I'm missing here many of them, obviously also the many supporters from funding agencies, and I hope we still have time for one or two questions, and thank you very much for your attention.
Thank you very much, Sami. Really interesting talk as always. We have a couple of questions, but due to some time constraints, probably I will just ask one if it's okay with you. So one of the questions, which was also reposted by several others, came from Chiro, but which is who asks, in what you call isolation phase within the collision monitoring pipeline, don't you think that the identification of the contact point is still a challenge using only proprioceptive sensing? And it follows, you can identify only the link where the contact is happening, right? And how about multiple contacts? How could you tackle this problem?
Okay, so Chiro obviously has a very good point here. So I think what is important in the collision monitoring framework is really that this is not depending on the particular sensing setup. This is rather kind of the general framework. And obviously, detecting and isolating collisions, or multiple collisions, and also the ones that are kind of absorbed by the kernel of the Jacobian, you essentially cannot see. And obviously depends heavily on the specific sensor setup. So if you take only the standard measurements, then obviously there's severe restrictions. So the more joints you have, the more you can see, obviously, but obviously not many contacts. So yes, this is exactly what our paper will be about, that we hope to publish this year. That exactly can tell you for tree-like structures, given a sensing setup, so also placing multiple force torque sensors, how many contacts can you see, where can you see them, and so on and so forth. But I think in general, these are two different questions in a way, and they come together if you then kind of try to say, given my current method, how many of these parts can I actually answer? So isolation, obviously, if you have 6 sensors, then the question is, what kind of contacts are you dealing with? Are you dealing with force contacts only, so collisions, you typically have forces only, or do we deal with full wrenches? Then obviously we need more degrees of freedom in the contact to see it. And obviously the next step we would be taking, and obviously this is a thing that still needs to be done. How do you fuse tactile sensing and proprioceptive sensing to really get best of all the different worlds, right? So I tried to show that also with classical proprioceptive sensing, we, for example, didn't get the best of what we could do. I mean, using the IMU in the joints and infusing it, really, we could actually get rid of the whole problem of velocity and acceleration measurements, use standard direct methods, and maybe even at some point make the monitoring method by momentum observer obsolete. Let's see. So I think this is something that obviously has a more than valid point. We're just trying to take it step by step and really be also sure if we then later on fuse it proprioceptive with tactile sensation, that we have the optimal trade, not the optimal trade-off, but the optimal setup that makes best out of both directions. I think that's kind of my answer on that.
Okay, thank you very much, Sami. There are some more